Good morning, afternoon, evening to everyone who's joining us. Thank you for making the time today for our Snack and Learn webinar. My name is Scott Cumming. I'm a professional engineer with WSP Canada, based in Vancouver, British Columbia. And I'm actually really happy to be sharing with you today some of the work that we've been working on in recent months and years regarding design and procurement of low embodied carbon concrete. So just go over a quick agenda. We'll go over what is embodied carbon, talk about cement, concrete, greenhouse gas emissions, a little bit about how to determine the carbon intensity of concrete mixtures, a quick overview of some of the work we've got in progress, some design and procurement strategies, future opportunities, and we'll leave a few minutes at the end for some Q&A. So I've got quite a number of slides, so I'll have to go fairly quickly, but here we go. Embodied carbon of concrete. What is it? We're really most interested in the embodied carbon, or the CO2 emissions that are a result of extraction and manufacturing and transportation and construction, sometimes the end of life impacts, but what we're most interested in is the upfront carbon. We're not talking about the operational carbon that results from operation of a building or an infrastructure asset, such as the heating, the ventilation, the cooling, lighting. We're really most interested in the CO2 emissions that are a result of the building materials that are used for construction. And why is this important? Because as the facilities and buildings become more efficient into the future, the operational energy used to occupy, it was a disproportionate amount of the CO2 emissions in comparison to the embodied carbon. But with the time and designs for improving the operational efficiency of buildings, that slice of the pie has actually reduced in size, and over the coming years and decades, it will become nearly equivalent between the amount of CO2 emitted from the embodied carbon compared to the operational carbon for buildings in particular. And why is this important? A sooner reduction in the embodied carbon, it adds climate mitigation value. Think of it as a very short-term effective strategy that will have real-time impacts in the very near future, rather than having to wait 10, 20, 30 years into the future for these incremental decreases in the operational carbon to catch up to the overall total amount of embodied carbon that results from the original construction and some renovation later on. So it can have immediate impacts in the short term compared to some of the operational carbon that takes many decades to be realized. Cement, concrete, greenhouse gas emissions. This is extremely important for concrete because nearly all construction in the world requires concrete. For context, there is more than double the amount of concrete used for construction than all other building materials combined. Annually, there are about 4 billion tons of cement produced each year, and about 20 billion tons of concrete produced each year. And approximately 8% of the world's greenhouse gas emissions are the result of the manufacturing of the cement. And of that 8%, approximately 2/3 of it are a result of the calcination reaction that occurs during the manufacturing process, and the other third is a result of heating and combustion of fossil fuels that are used for heating of the kiln. And out of the kiln comes clinker that becomes mixed together with limestone gypsum equals Portland cement, mixed together with sand and gravel and water equals concrete. And what we're seeing in the last number of years is the introduction of limestone into that process to be interground with the clinker to reduce the amount of clinker that's actually in the Portland cement. So there are some immediate reductions that are occurring today in the cement manufacturing process. But of that, to reduce the amount of cement that's consumed and to reduce the amount of emissions that are a result of the cement manufacturing process, we can't really do much about the fossil fuels except switching or transitioning to lower carbon fuels, or by waste heat recovery, capturing the heat from the back end and re-injecting it at the front end. The main impact that can be realized is by reduction of the Portland cements that is consumed in concrete. Whether it's substitution, use of blended cements, using supplementary cementing materials such as fly ash or slags, optimizing designs, improving efficiencies. Why are we designing 50 megapascal concrete if we only need 35, for example? And certainly as we move into the future, the use of carbon capture technologies will be also extremely important to target combustion emissions. And even though in the volume of a concrete, Portland cement only occupies in the order of 7 to 15% by mass of a cubic meter of concrete or cubic yard, it accounts for nearly 80 to 85% of the total carbon footprint of the concrete. So it's certainly a disproportionate amount compared to the volume that it occupies in the concrete. Now, how to determine the carbon intensity of concrete? It's a very complex problem to understand because the concrete is a mixture of several different ingredients. The paste is the different cementing materials, aggregates, various admixtures, water, of course. And the challenge would be that each concrete supplier may actually produce dozens of different concrete mixtures in different recipes on any given day, supplied to project sites all over the geographic region they serve. And the carbon intensity of the different concrete constituents does vary quite substantially. And the impact that can be seen here relative to Portland cement, some of them are minuscule in comparison. In the embodied energy, if you look at the embodied energy in this particular slide, the cement is in the order of 85% of the embodied energy, whereas the aggregate is even less than the amount of CO2 emissions that it takes to transport the concrete from the batch plant to the job site. So it is a very large amount. Environmental product declarations are becoming very common. They're similar for those who don't understand what they are. They're similar to nutrition labels that you see on the packaging of food products, and they outline certain the impact that certain concrete mix designs have on the environment. And the most important metric which we're talking about today is the global warming potential, which is expressed typically in units of kilograms of CO2 per cubic meter. And some ready-mix concrete manufacturers have actually undertaken investment in producing product-specific EPDs from various batch plants. These are typically available on their websites, but in various regions, the ready-mix concrete associations in both Canada and the United States have actually developed regionally specific environmental product declarations, which have they've solicited data from several different manufacturers and put together basically industry-wide averages. And right now, the American baseline, I think, is an average of about 7 or 8 different geographic regions in the United States. Canada has actually gone a step further. Just recently, last year, released industry-wide EPDs for 7 different geographic regions. And these can be used to actually get an idea of what are the real impacts of the concrete mixes that are produced and supplied in those regions, and based on the use of local materials. These are all actually available for free download. The link is here. Again, that'll be in the slide deck at the end, so you're more than welcome to click on some of these links and find them. But what is the baseline to which we're comparing when we're trying to determine whether we've actually managed to reduce the embodied carbon of the concrete? That's not an easy question because for the carbon intensity, it can be affected by several different factors: strength, the aggregates, the type of cement that's used, from where the materials originated, what the local energy sources are at the batch plant and the cement kiln. And there's really quite a wide range depending on the strength class for all the different geographic regions. And part of what the regionally specific baselines have actually done is issued what they believe to be baseline mixes that can be used for comparison. This is just one example from I've taken out of the Concrete Ontario baseline, and they've suggested the baseline here highlighted in the pink and various iterations with increasing amounts of slag and concrete mixes with or without air. The challenge with some of these baselines is the data was taken from, I think it was averages of concrete batch plants in 2020, when a lot of concrete was still produced with type GU cements or type 1 in the United States. SEM 1 and parts of Europe is similar chemistry. But we've seen in the last couple of years nearly a total transition to the use of Portland limestone cements, which will already have an immediate reduction in the global warming potential in the order of 6 to 9%. So already these baselines are somewhat higher than what is now commonly used for production of concrete. And we think that what should be reasonably achievable target baselines can already be shifted. This is like the same mix class right here compared to here. You can already see that there's been a reduction of about 20 kgs of CO2 emissions just by the simple switch from Portland cement to Portland limestone cement. So what we've actually done at WSP in the last couple of years is we've actually developed a tool, a concrete embodied carbon estimator, where it actually really helps to envision what is the global warming potential impact of the different projects that we're working on. And it basically establishes a carbon budget for each individual project. It allows the users to enter the concrete mix, the intended use, the approximate volume of concrete to be placed, and then from the various different baselines, the baselines can be tailored to whatever geographic region the project is located, and selected from a drop-down menu what is the baseline. And then from that, it'll take the total volume of concrete for the mix, or for the project, pardon me. And the users can also enter their own concrete mix proportions and see how their mixes might compare to the baselines. And from there, it will also calculate for 12, 15, 20 different mixes. And the weighted average of the different volumes, what the global warming potential is for the entire project. In this case, this particular example project is in the order of 14 million kilograms of CO2 to be released, 14,000 tons as the total impact of the concrete used for this project. And based on the regionally specific baselines, and then what we believe should be reasonably achievable, already results in a 17.6% reduction in comparison to those numbers. So it allows the user to actually toggle around and decide which of these mixes may they want to target to reduce the overall impact of the GWP on their project. You can see here 20,000 cubic meters of concrete for footings in comparison to 500 cubic meters of shotcrete would have a much larger impact if the targeted efforts for reduction of the GWP were focused on the larger volumes of concrete. So that's some of the work that we've been working on. This one is actually currently in use at the Canadian Parliament Center Block Rehabilitation Project in Ottawa. It's been internally developed and is being used to support procurement of low carbon concrete for the Center Block and the Public Welcome Center projects. Overall, PSPC, the government agency for procurement in Canada, is looking to significantly reduce the carbon emissions, both embodied and operational carbon from some of the assets in their inventory. That's just a little bit about this project. There's more information that can be found clicking these links that are in the slide. And also at the present time, we're working with the Vancouver Airport Authority to estimate the GWP from recent airside infrastructure construction projects. And after we've completed that inventory in the next couple of weeks, we'll work together to identify opportunities and strategies for reduction of GWP for future projects. We believe that the estimation that can be achieved will provide a significant contribution to the airport's net zero by 2030 objectives. So design and procurement strategies, I think this is what a lot of people are interested in. By far the most effective approach is ensuring that the specifications and the designs are performance-based approach. The engineers, the designers will still provide requirements for structural, durability, aesthetic requirements, but really leaving the how. How are we going to achieve that? To the contractor, the concrete supplier, materials engineers, and leave it to them to optimize the concrete mixtures and construction methodologies, rather than telling them put this much cement, put this much water, put this much aggregate in the mix and provide it. What we really need to see to advance this procurement process is to remove prescriptive specification requirements wherever possible, because frankly, they actually stifle innovation and products and approaches. And in addition to the typical requirements for structural durability and aesthetic performance, also provide a specified requirement for the submission of EPDs for each concrete mixture, and also the provision of benchmark average unit values for embodied carbon for various concrete strengths in local regions. And then also provide a total embodied carbon reduction target for the project, instead of micromanaging the project and requiring a reduction for each mix. And it can really allow for a tailored reduction by the element. So easy first steps: make sure that specifications allow the use of Portland limestone cements. That's first and foremost. Type GUL in Canada, type 1L in the United States, that should already be there. It's already in the back of the concrete trucks showing up at the job site, whether you're aware of it or not, it's already there. But in addition to that, making sure that the use of Portland limestone cements and supplementary materials such as slag, fly ash are allowed to be used together. They work together, they're very effective together. And instead of just Portland limestone cements on their own, you might achieve a 6.5% reduction. Using them using them together with supplementary cement materials, you can achieve significant reductions up to 25 to 30% in this particular example, and making sure we maximize the use of supplementary cementing materials. There's some benefits of the SCM listed there. Basically, think of it as, let's think of and technologies. Let's pull every lever that we possibly can to reduce the GWP in concrete. And we're not really interested in, oh, we're going to use this approach or that one. We want to use all of them together and combine as many of the reduction strategies as we possibly can. And ensure that all of the specifications allow for all available technologies, provide standards and product category rules for EPDs that must be followed, define the baseline that is to be used by all bidders, and specify the maximum greenhouse gas intensity that is to be used for the total volume of concrete. So in essence, again, the designer specifies the strength, the exposure class, durability, maximum product embodied carbon budget, and leave it to the contractor, the concrete supplier, the materials engineers to determine the mixed proportions, the types of cements, et cetera, that will achieve those specified requirements. And what we really need to actually achieve these objectives is leadership, and we're starting to see it from the federal government. In Canada, government infrastructure projects consume approximately 40% of the cement produced globally, pardon me, not just in Canada, but globally. And it really will be up to the governments and owners to drive the demand for this, and requiring increasingly lower carbon materials and procurement, adopting performance-based approaches. They're incentivizing innovation. So the Canadian Treasury Board Secretariat published procurement requirements in late 2022, and they're committed to reducing the greenhouse gas emissions from concrete by more than 15 megatons by 2030, with ongoing annual reductions of more than 4 megatons beyond that. So there's a roadmap that was issued late last year. Same thing. Requirements for the US government, the General Services Administration have implemented requirements for the use of low carbon concrete as well. And the limits for the global warming potential must be less than 20% of the new building institute's proposed 75th percentile. So there's more information that can be found in either of these two documents, but that's really where it's being driven right now, is the federal governments, at least in the United States and Canada, insisting that federal money used for procurement of concrete actually procure low carbon concrete. So it is also recognized that sometimes the use of high volume supplementary cemented materials do have some trade-offs. Usually there's a carbon reduction, but there's a slower hydration, strength gain, set times. So it does need to be a holistic approach with the concrete suppliers, the contractors, review the schedule, pre-qualify the mix. Sometimes there might be a little bit of trial testing required and additional curing requirements. And in some instances, there's higher least strength requirements for various projects. So there are some language, there is some language in the Canadian and American guidelines for relaxation of the requirements for higher least strength or cold weather placement requirements. The challenge is there's no arbiter who decides what really is necessary for higher least strength, or what really defines what is cold weather and when the relaxation should be allowed. So there's a little bit of work to be done. It's a great start, it's a good framework, but it could be tightened up in future revisions. So anyways, future procurement strategies, really make sure that the minimum bid options are compliant with the specified maximum GWP contributed by the concrete for the project. And if it's of interest, bidders may be able to propose even further reductions if they're capable, and then provide a formula for evaluation and score for the client. The client can decide if the additional carbon reduction of their concrete is worth the extra money to them that it might cost. Sometimes it might cost a little bit more, other times it won't. Can allow them to exercise that option or not. So just a little bit about the future work that we've got going on. Manufacturing optimizations, we can improve the facility energy efficiencies, switching over fossil fuels to alternative energy sources at the cement kilns. Construction execution, it really requires early stage involvement and buy-in from all parties to achieve it, because there may be an impact on the setting time, the finishability. Ambient conditions can have a large impact on that. And in the future, there will be definitely a need for carbon sequestration opportunities, capture of CO2 from the cement production, and also injection of CO2 into plastic concrete for mineralization. So one of the current approaches we talked about, the use of Portland limestone cements, can typically achieve a 5 to 10% reduction right off the bat. These are already code approved. They're readily available throughout Canada and Europe, and certainly becoming widely available in the United States, and certainly should be used together with supplementary cementing materials. Future approaches may include carbon mineralization in concrete. We've even seen a cement kiln in Mexico that is now harnessed solar energy by using a mirror field and concentrating that heat into the cement kiln. Recently, we've seen the use of crushed recycled glass as a pozzolanic material, and that should be becoming code approved in the very near future, if not already. And even some carbon negative cements that are chemically and physically identical to Portland cement. There's a patented manufacturing process that does not emit CO2, and it's the hope that that can become more mainstream and commercially viable in the not too distant future. Even synthetic aggregates are being produced as well. Some of the projects that WSP is currently working on, we have been engaged by Heidelberg Materials for some major upgrades at the cement kiln in Edmonton, Alberta, to develop the first full-scale application of CCUS in North America, and leveraging this technology has the potential to reduce the GWP of concrete by 90 to 95%. So we're pretty excited about that opportunity. Quick summary, embodied carbon content of concrete can easily be reduced. We just need to be mindful of the benchmark that's used for evaluation and comparison of the GWP. It's very important. Wherever the benchmark is, that's the number that we're using for measurement of how much reduction have we achieved? And there's going to be several approaches that are available in the future, and there's quite a number of them that are already available now. Procurement strategies, I can't emphasize this enough, should be using performance-based approaches for design. Establish a carbon budget for the project based on the amount of concrete to be used for construction. Allow the suppliers, contractors, materials engineers to identify the optimal approach, and certainly combined strategies can achieve the significant CO2 reduction. And the tool that we've developed is certainly available and can be used to quantify and verify the embodied carbon content of concrete mixes and allow for evaluation of alternatives. And with that, I thank you for joining us, and I'll certainly be happy to answer any questions that people might have. So.
Thank you, Scott, for a fantastic presentation. We just have a few minutes for a couple of questions. Just to mention quickly that the presentation slides are available to download in the handout box on the GoToWebinar control panel. I will start with the first question. Is there any reason to specify only type GUL cement, or do we need to still allow type GU cement?
There really should not be any reason anymore for the specification for type GU cements. They have, at least in Canada, have been identified as being equivalent. Usually, some people think that the GU cement may be a watered down version of the GUL cement may be a watered down version of the GU because it's the same amount of clinker, just with additional limestone. So if we've got less clinker, then it must be watered down. That's not actually the case. The clinker is now ground to a finer consistency than the GU cement, so that the strength activity remains approximately the same. So if two concrete trucks show up at the job site, one with a GU cement in the back, the other with a GUL cement in the back, the people at the back end of the concrete truck should not be able to tell the difference, and there should be very modest, if any, difference in the plastic and the elastic properties that result.
Thank you. The next question is, are there any up-to-date studies on the variance in embodied carbon of mixes between different regions?
Certainly, I mean, the ones that I've put in the links, those are probably the best ones right now for the different geographic regions in Canada. Those ones were done, I think it's based on 2020 to 21 data, and those were produced in 2022. But for an EPD to be valid, they do need to be updated every 5 years. So there is a fantastic database that's available on the various websites. ASTM is actually a good resource, and a lot of the concrete manufacturers, if they've invested in these, have the links posted right on their websites, and anytime that they're updated, they're available right there. But yes, the regionally specific ones are probably the best source because, for example, in Alberta, there's a lot of fly ash used for concrete production and very little slag cement, but in parts of Ontario and Eastern Canada, it's almost entirely slag cement and very little, if any, fly ash. So having one report for Canada would be very unhelpful because of the availability of local materials in different regions. So.
Thank you. I will take the last question. Are sample specifications available for further reference?
There are some that different regional governments have issued. Marin County in California is certainly one. Part of the challenge that the industry is facing right now is there's several different local governments who are all racing to try and develop their own standards, and there's really a limited amount of guidance available, and there really needs to be a concise and consolidated approach to what is the ideal approach, because some of the approaches that are being taken by various regional governments are somewhat misguided or establishing baselines that are very challenging and difficult to achieve in reality, and just because it's written on a piece of paper does not make it actually achievable or constructible. And that's where some of the governing bodies like Canadian Standards Association will be working on an accelerated guidelines in the next year or two to get that out, recognizing that it needs to be sooner than the typical 5-year turnaround, because the next revision to the CSA standard will be issued in 2024. And even then, there's a 5-year cycle before those changes are incorporated into the National Building Code of Canada, and then the different regional building codes. And part of the challenge is that the building codes are established as minimum requirements, and they're primarily focused on life safety, and they've been very slow on the uptake of the environmental responsibility into things. So there does need to be some additional work on the codes and standards. But the sample specifications, the Marin County one in California, is actually a pretty good one at the moment. So.
Fantastic. Thank you, Scott, for a fantastic presentation. Apologies, we don't have time to cover all your questions. Thank you for submitting them, and Scott will be following up with you via email later on this week. So thanks again, everyone, for joining. Please feel free to follow up directly with Scott via the contact details shown on the screen. And I wish everyone a wonderful day.
Thank you for your time. Have a great day.
Thank you so much, everyone.